of the Experimental Mathematics Seminar at Rutgers University. Today's speaker is a renowned experimental mathematician, Doron, who will speak about, the official title is How to Extend Karolyi and Nagy's Brilliant Proof of the Zeilberger-Bressoud q-Dyson Theorem. But the true title is How the most proud humanly derived theorem that I proved way back when I was young turned out to be almost a triviality. So I think this is the fate probably of most human proofs. That's why our hope of getting generally deep results lies in computer proofs. For example, if I take a permanent, a 100 by 100 permanence of 0 and 1 matrix and find the exact value, this will be a much different result than the famous last theorem, because human mathematicians only do trivial things. So let me explain first what it's all about. It all started with one of the greatest physicists alive today, Freeman Dyson. Freeman Dyson is one of my greatest heroes. In fact, this talk, the paper and the talk is dedicated to him on the occasion of his 89.7th birthday. He's going to be a 90-year-old on December 15th, and he's still going strong. He just published a paper about game theory, revolutionizing game theory about a year ago, and it's amazing. And he's a mathematician, physicist, and also a political figure, very strong opinions, and it's really an amazing thing. Anyway, one of the things that he conjectured way back in 1962, it became known as a Dyson conjecture, was the following innocent. Take this product, that you have n variables, x1 through xn, and form the following product. This is not too bad. Now raise it to the a's power and expand it. You get a huge polynomial with n variables. With n equals 4 and a equals 5, nowadays Maple can do it. And ask for the coefficient of x1 to the power 0, xn to the power 0. In other words, ask for the so-called constant term. That's why it's called the Dyson constant term conjecture. And surprise, surprise, we have a beautiful, nice, explicit answers. As explicit as it can get. It's na factorial over a factorial n. There was the original Dyson constant term conjecture. And then he had, in the same paper, he had something a little bit more general. Instead of having only A, he had, I think it was AI and a J. So you have also integers and A1. So for this more general one, you had the multinomial coefficient, A1 plus AN. And as usual, the more general it is, the easier it is to prove. So this conjecture did not last very long. But Dyson could do it for a special case, n equals 3, maybe n equals 4, I don't know. By the way, this was a very important paper for other reasons, not because of this reason. In this paper, it was about the statistical theory of energy levels of some atoms. So he had some distributions, and a few years later, the number theorist, U. Montgomery, went to the Institute for Advanced Study and tell him about some conjectures about the distributions of the zeros of the Riemann zeta functions that he did numerically. And then Dyson said, it looks familiar. That's exactly the distribution that I conjecture in this paper, and this led the whole cottage industry of relating spectra of energy that came up in physics to zeros of the Riemann zeta function. All conjectural. Nobody had any clue how to prove it. But we are famous, people make a living by thus making nice conjectures, but the very deep relations between this. And Andrew Zisco refined it, and many other people refined it. So this paper is famous for other reasons. But it's also came this conjecture. So this conjecture did not last very long. A young and brilliant postdoc called Kenneth G. Wilson, about a year later or maybe less, found a proof, very ugly, very complicated, 4 pages of heavy calculations, but it was a proof.
Not bad for a physicist, no?
Huh? Yeah. And that he was an obscure postdoc. Another obscure postdoc by the name of John or Jack Gunson also independently proved it. And they both published it in the same Journal of Mathematical Physics, about a year after Dyson's paper. This guy, as far as I know, is still fairly obscure. I tried to Google him. He had a nice career, but he never got a Nobel Prize. But this guy got a Nobel Prize. He invented or discovered the renormalization group theory that revolutionized statistical mechanics and other things. So this guy went to do bigger and better things. But the proof of the book of this conjecture came up in 1970 by one of my other heroes, Jack or I.J. Good, the great probabilist Bayesian probabilitist, whose other claim to fame was he was a colleague and friend, or I don't know about friend, but a colleague, at least a colleague, maybe friend, of Alan Turing. He was in the Enigma project, he was very instrumental, and he was in the so-called war effort with Leslie Park. So in 1970, he came for the proof of the book of this that I loved. And ironically, if you look at this Nobel Prize winner's paper, Good's proof is implicit in this. He had a relationship, a lemma that really was the crux of this. So let me tell Jack Good's proof very briefly. What happened, forget about the constant term for now. Call this f of a1 the function an, and suppress the dependence on this thing. Now, Jack Good, being a Bayesian probabilitist, knew the property that the multinomial coefficients satisfy the beautiful recurrence. So let's call this G of A1 again. So the combinatorial interpretation of this is a number of walks of going from the origin to the point A1, A2, An in the n-dimensional square or cubic, n-dimensional hypercubic lattice. If you walk from the origin to the point A1, An, this is the number. Because how? Because you want to choose. It's like choosing after A1 plus A2 plus An steps. You choose how many should I go in the one direction, in two directions, and so on. So since the number of ways of going from the origin to A1 An, the last step, you were either at this point, or you go at this point, since you're walking on the lattice. Oh, so that's also it's a trivial to prove it algebraically. An minus 1. So this, obviously, the right-hand side satisfies this. And the initial conditions are easy. Thus, when A1 is 0, it's the same thing with n minus 1. Then Jekyll said, let's try to see if this whole thing, the constant termand, also satisfies it. So you plug it in, and surprise, it does. And the proof is that the trivial application of Lagrange interpolation formula. So all he did, and the same relationship is in Nobel Prize winning Ken Wilson's paper, this relation. But I didn't realize that this implies right away by induction. So you take this, you simplify, you get a trivial algebraic identity that is equivalent to the Lagrange interpolation formula. And then, since it's true for this and this recurrence, so now we have f. So it's also true for f, for the function itself. And since this is constant coefficients, there are no dependence on x1, x2 to the xn. You can take the constant term for both sides. So both this right-hand side and the constant term of this satisfy exactly the same recurrence and the boundary conditions QED by induction on A1 plus AN. So this was good, beautiful proof from the book. But then in 1975, another smart hero of mine, George Andrews. He's a friend, but he's also an enemy. He's a personal friend, but he's an ideological enemy. He's a super conservative, old-style mathematician who believes in rigorous standard human proofs. Also, he likes analysis more than he should. So I like him very much, but I also hate him very much in ideology. And vice versa, I think Mucha. He loves me as a person, but he hates my views. So it's nice to have a love-hate relationship. Anyway, he is Mr. Q. His claim to fame, whenever he sees something, he replaces his stick a Q. So he's a master of Q analogs. That's his claim to fame. So what's the Q analog of a power? Okay, first, n factorial. What's n factorial? 1 times 2 times 3 times n. What's the Q analog of an integer, I? It's simply 1 plus q squared plus q to the I minus 1, denoted by I bracket. So it's a geometrical series. And if you went to high school, you know you can simplify it like this. So that's the Q analog. So it's like inflation. If you count, if you make the same amount of money every day, then you have I dollars after I days. But if you have inflation, and Q is less than 1, unfortunately, then eventually that's how much you have. So the Q analog of this is just the Q analog of 1 minus x to the power, I don't know, let's call it n. 1 minus x times 1 minus qx times 1 minus q to the power n minus 1x. So that's the dictionary. That's the dictionary between 1 minus x to the power n, between ordinary and q. And the shorthand for this is, that's the shorthand, x sub n. It's not very good shorthand, but usually the full shorthand is x semicolon q sub n. But if it's the same q, that's called the base. With the same q, you don't put it. So what George Andrews did is look at this and do the Q analog game. He first tried this. A sub I, and then x sub j over x sub I sub aj. And this didn't work. You get something ugly. You experimented. It's not nothing nice.
It's not the Q-Snell coefficient.
Yeah, no. If you do, it is. No, if you do this, the obvious thing, the most obvious thing, you replace the art of Q analogizing is, if you have 1 minus x to the power something, you replace by x sub n. So the most natural thing would be to replace what we had before, 1 minus x I over xj to the power of ai by xi. So that's the most natural thing. And the constant term of this is not nice. But what's nice about q, then when q equals 1, it is 1. So if you do this, when q equals 1, you still get back the Dyson thing. And now, lo and behold, you got this. And Zoltan tried very hard, he couldn't prove it. He proved it for the special case n equals 3. When n equals 3, it's a classical identity called q-Dyson. Q-Dixon, sorry. Q-Dixon. Dyson already did the n equals 3 case. For the ordinary case, the n equals 3 case is a classical identity called Dixon. Okay, let me tell you what Dixon is. This is the classical number coefficient identity, I think, was discovered around 1900. May 1900. The Dixon identity. It's a beautiful binomial coefficient identity. Minus 1 to the power k, a plus b is one of my favorites. Of course, now my beloved solved B1 can prove it in a nanosecond, but it's nevertheless still nice. B plus k. So this binomial coefficient sum for whatever negative into infinity with the convention is a trinomial coefficient, because that's a special case. So if you do trivial manipulations, the special case of Dyson n equals 3 is this. And Dyson noticed it. And that's how he proved the special case n equals 3. And it's very possible, I don't remember, maybe he also did n equals 4. So when George Andrews proposed this, he right away could prove n equals 3. Because it's q-Dyson. Q-Dyson was proved by somebody called Jackson in 1910. So it was already known. So it made sense for n equals 3. Andrews knew it was. But nobody had any clue how to prove it for arbitrary n. Then one of George Andrews' students, Kevin Cadell, with a 50-page paper, proved n equals 4. Then in 1982, when I was young and handsome, I found a new proof of Dyson, of the original Dyson, a combinatorial proof, using tournaments. I don't have time to describe it, you can look it up. Nice, elegant proof, inspired both by Dominique Foata. Dominique Foata had a combinatorial proof of this, with tournaments. And Ira Gesser had a combinatorial proof of the very special case where all the i's are 1. Then it's essentially the Van der Monde determinant identity. And he had a nice tournament. So by morphing for Foata's proof for k n equals 3 and Gesser's proof for all the a's being 1, I found a nice, a little bit longer than Jack Good. But what's nice about it, it was natural, it was combinatorial, and it was elegant, also maybe 4 pages using tournaments. And I was kind of proud of it. But the main motivation was I was hoping to extend it to prove the still open q-Dyson conjecture. And I tried very, very hard, and finally I succeeded. But then there was a pretty big gap in the proof, noticed by Zeilberger-Bressoud. And Zeilberger-Bressoud fixed this gap. And Zeilberger-Bressoud generously insisted that the paper will be even not alphabetical. So that's why it's one of the few theorems in mathematics in which it's not cryptographic. So this became the Zeilberger-Bressoud theorem. the q-Dyson conjecture became the Zeilberger-Bressoud theorem because it was my proof with a major gap filled by Bressoud. My original proof was not too bad, was maybe 8 pages. But once Bressoud filled the gap, it was about 22 pages. And George Andrews very, very generously called it an astounding tour de force. And I was very proud of it. And I was hoping that nobody will ever find a simple proof. And what's nice about it was an example where a combinatorial proof was the first proof of this. Usually you have a proof using algebra or analysis, and then some combinatorialists come up, a new elegant combinatorial proof of blah, 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 blah. So but in this case, combinatorics was a tool for finding the first proof. So it was a landmark case, I think, of the combinatorial techniques were used to give the first proof of this. And I was hoping that nobody will ever find a simpler proof. But then John Cambridge, a former student of Peter Stanley in his dissertation, found a much simpler proof, but for the special case where all the AIs are the same. But nobody could find a simple proof in general. Then about 8 years ago, or maybe 7 years ago, Ira Gessel and Jussi Zinn, a former student, found a simpler proof about a 10-page proof instead of 22 proof, an algebraic proof. Fairly elegant, but not too elegant. It was fairly hairy, and he had to work very hard to figure out all the details. So it was a little bit disappointing that you can do it in 10 pages instead of 22 pages, but still, it was not yet trivial. You cannot call it trivial. But then, to my great horror, about 7 months ago, Dennis Stanton, in fact, told me, did you hear about so-and-so's, about the Karolyi and Nagy's proof that made the q-Dyson, the famous Zeilberger-Bressoud theorem? Almost. It was polite. It didn't say a triviality. It's a simple, nice, a simpler. We called it a simpler proof. It was diplomatic. It should have said a trivial, almost trivial proof. And I didn't, but obviously I was curious. I sent email to these people, and they reluctantly gave me the copy of the paper, and the purpose, the rest of the time, I will describe they are beautiful. Absolutely beautiful. It's not completely trivial. It's still 1 page, or maybe 2 pages, if you explain everything. But it's really brilliant. The original q-Dyson, one natural thing would be to use induction. Nobody was able to do the good, to find a q-good proof, to generalize that good proof by induction. Nobody could do it. Maybe there exists one, but nobody can do it. But the beauty of this, you don't need any recurrence. And the irony is, they use the same old dirty trick. Jack Good used Lagrange interpolation formula. So what these guys use, let me write the names. Karolyi, Gyula, it's Hungarian, so I have these accents. And Doron and Nagy. Sorry, Zoltan. And Zoltan, they're my heroes. Well, I hate them, but they're my heroes. Zoltan Lorant and Nagy. Two aliens alias Hungarians, who found the proof from the book to the Zeilberger-Bressoud q-Dyson theorem that the constant term of this is this. And what they used was another dirty trick in combinatorics. In 1999, Noga alone pretty much revolutionized extremal combinatorics by coining something that, once again, like all great discoveries, by hindsight is almost trivial. It's called the combinatorial Nullstellensatz. And he found lots of nice, apparently deep, seemingly deep results. They were open for many years. You can prove them in a few lines using the combinatorial Nullstellensatz. I'll tell you what it is in a second. But then about a year ago, a few people found, I forgot who they are, but it's in the paper, the quantitative version of the combinatorial Nullstellensatz. So let me tell you what it is. So the combinatorial, the quantitative version. So it is stronger because it gives you some information. So once again, it's about a polynomial, about an innocent polynomial. So here's the statement of the quantitative form of the combinatorial Nullstellensatz. Sorry, quantitative. The quantitative version of combinatorial Nullstellensatz. It's about simple polynomials in many variables. So let f of x1 and xn be any polynomial of degree d1 smaller or equal to d1 plus d2. So d1, d2, dn are non-negative integers. And you come up with a certain polynomial f of x1 xn of degree smaller or equal to d1 plus d2 dn. Now the beauty of this theorem, it's so general. As you know in mathematics, the more general it is, the easier it is to prove. So in this case, it's very general. So let A1, A2, an be any set of numbers or symbols even, A1 be any sets. The only condition is that the cardinality of AI is di plus 1. So the input is a polynomial in many variables, x1 to xn, and you have the degrees, non-negative integers, d1 to dn, and you have some polynomials. And the other input is n sets of numbers, a1, a2, or members of a field, where the number of elements in AI is one more than di. Now, the coefficient, so it already looks relevant. The coefficient of x1 to the power d1, x to the power d2, x sub n, d to the power n, is given by an ugly, horrible expression as follows. A huge, huge, huge multisum. Sigma, sigma, sigma. C1 belongs to A1. C2 belongs to A2. And Cn belongs to An. So you have n sigmas. The first sigma ranges over the set A1. Second sigma over set A2. And here comes the summand. Capital F, the same polynomial, f, evaluated at a typical point, C1, C2, in this Cartesian product. So it's a Cartesian product divided by the following. Phi sub 1, I'll tell you what phi sub 1 is in a second. Phi sub 1 prime of C1, phi sub 2 prime of C2, phi sub n prime of Cn. But I still have to tell you what is phi 1, phi 2, phi 3. So please, here we go. Phi sub I of Z is the following.